afterwards, he was recruited by the IOL lab, and he will tell us very interesting things about the microlayer between the ocean and the atmosphere.
Okay. It's okay. I need a mic, or this one is connected. Thank you, Yoav. My name is Peleg, as Yoav said, and I'll be showing you details about my recent research dealing with the sea surface microlayer. And this is the point, and it goes. Okay. This is a Windows 10 service pack. Highly recommended. Anyway, the sea surface microlayer is literally a blanket that spreads over all aquatic bodies elsewhere in the world. And in this case, it's just as some kind of an example. If you take olive oil, for instance, which is an organic compound by all means, and you mix it with water and you create some kind of a mixture, you are familiar with this one. If you do a salad, it's all the same. And then you pour it into a separating funnel or any vessel that is transparent. Immediately you see that there are two phases, and one of them sits on top, which is the organic phase in this case, and the other one is water. And there you have it. It's the same phenomenon happens when you have an oil spill, for instance, which is also some kind of an organic component of oil. And what actually happens is that the microlayer, or the film that sits above the water, is now thickened. How thickened is it? By a few, or less than maybe twice. So how thick is the surface microlayer when there is no pollution? Well, the thickness is approximately between 1 and 100 micrometers. And bear in mind that since 70% of the world is water, that's a great amount of water or compounds, you name it. Approximately 70% of the world is the microlayer of the surface area, that is. Let's discuss about what's in it. Well, it is highly enriched with surfactants. We know that, and I'll show you a few examples in the next few slides. And it is assumed that surfactants control in an indirect way the gas transport in and out the water. Also, it is a special habitat. We'll discuss this issue. Also, of bacterial and phytoneuston. Neuston is another name for SML, for the sea surface microlayer. And, of course, the home of other creatures also, such as larvae of mosquitoes and of fish. Also, I'll show you some details about where I'm heading to with this approach of aerosol that has some kind of airborne contribution to the SML. And last one I'll show you is the pollution of highly hydrophobic components. Now, this is an example of how you sample the microlayer. This is the classical way, which is pretty good, I must admit, but it has its flaws. If you're familiar with the term Langmuir blot, that's the exact same thing. What happens is that you dip some kind of a hydrophilic plate, which is, it could be very well a ceramic or a glass. In this case, it's a glass plate. It's hydrophilic due to the fact that it includes silicon hydroxide residues on the surface area. On the first dip into a mixture of highly enriched surfactants, what happens is, any of you don't know what surfactant is. A surfactant is a molecule that is amphiphilic. One side of the molecule is polar, and the other one is hydrophobic. And so on the first dip, what happens is that the hydrophilic tails of the molecule itself, of the surfactant, attaches to the silicon oxide due to hydrogen bonds, and by this, revealing the hydrophobic end outside. Then the facing out. And then the next few dips, you do it slowly, of course, will fish out more hydrophobic molecules that otherwise would have been neglected, stay in the water. And all that is left is just to wipe it up into your vessel. Okay, my research goals mainly, I deal with organic chemistry, and what I do is I try to understand, to cohere, to have some kind of notion what are the compounds that stay in the microlayer, compounds that get enriched in the microlayer, to understand how the different mechanisms, approaches, how the different seasons impact on this layer N of the chemical arsenal, and also evaluate different sources and origins such as aerosol and urban runoff. Okay? This representation was I accepted this representation from, I got this one from Oliver Whirl, friend, and it was published already. It's not the wholly truth, but it's some kind of representation of what happens worldwide. What actually he did is he took MODIS ocean colors data. MODIS is a satellite. It is now, I think, is deceased. But it takes fluorescence images of Earth, and it's given, it used to be given for free in the net, and for each chlorophyll concentration that he could gain from the data of MODIS satellite pictures, he correlated surfactants in situ, that is, in sight on Earth, surfactants concentration due to a sampling cruise of its own. Now, he did more than 300 different cruises, and then he could correlate for each chlorophyll concentration the surfactant concentration, and by doing this, he could create these maps. What you can see that at the end of the day, you can see that in the equator, there is a low concentration most of the year of surfactants. The color, I don't think he picked the right colors, but be as it may. You can see that on the Northern Sea, you can see in blue, which is very high concentration of surfactants, takes effect in the summer and the fall time. Okay, maybe due to algal bloom or phytoplankton growth. Okay. You can't mention the sea surface microlayer without talking about surface tension. I'm not an expert in this field, but as far as I understand, this is the force that was created this is the tension that has been created by forces that push each and every molecule that is on the surface down. Let's say that you are a molecule of water, and if you are submerged, you have other molecules of water in your perimeter, and the NATO force of attraction of your molecule to the others is NATO 0, since it is attracted to all directions. But that's not the case in the surface microlayer. Since you see nothing but air above, the NATO forces bring you down, pointing down. And I don't have a lot of time to elaborate on this one, but the outcome of this one is, for instance, the bubble shape of water drips or soap bubbles. And since there's no bubble shape on the sea surface microlayer, but there is some kind of a surface tension that is being created that pushes pushes back each and every force that try to get deep down inside and to break it. For instance, I think it's called water striders, Jesus bug in Hebrew, I think. It's these bugs that can literally walk on water. They can do that since they don't break this surface tension. And don't try that at home, but what actually happens when you drip one drop of soap into the water, they'll immediately sink due to the fact that you added a surfactant. A surfactant is like a mediator between each and two water molecules. If one water molecule is here and another one here, and they have some kind of a mutual attraction due to hydrogen bonds, now all of a sudden you have in the middle a soluble molecule that is a surfactant, such as a soap. Then the forces are much lower, since the attraction forces between the surfactant and the water, and each one of the water molecules is much, much lower. This work has been done with the collaboration of Gilboa Arya from Ben Gurion, and you can see exactly what I mentioned now. If you take distilled water, you can see there was no need for a repeat in here because it's a well-known figure. the force is very high. This is the surface tension of each and every molecule in distilled water in 1 meter depth, which is the most used blank for microlayer experiments. The SSL subsurface layer, it's all the same. But even in 30 centimeters, it's all the same. It's the same surface tension. But it drops in the sea surface microlayer due to the fact that there are certain surfactants in an enrichment in the. This one was taken. Thank you. This one was taken 1 kilometer and a half from Shikmona coast. No, that's a good one, but we can elaborate on it. There are certain conditions that you can sample the sea surface microlayer, but it's in rather calm conditions, such as the waves under 30 centimeters and winds below 10 kilometers per hour. It's a pretty stable. This blanket is pretty stable. So, for instance, if you punch the water with your fist, then it will take a few seconds until it grows back again. Still, people avoid sampling only in those conditions only. Another thing is, another phenomenon that is highly related to surface tension is the creation of capillary waves. Now, capillary waves are small ripples, if you like, and those are by far the most abundant waves in the sea. Far more than the tsunami waves or the 1 meter wave. That's the most abundant wave in the sea. Now, it is a well-known fact for thousands of years that if you put 1 drop of soap in the water, then you can calm them down. And we'll see an example of that in the form of a slick. We'll discuss that further on. The thing is, gas transport in and out the water has been related more than once with the surface area. And so if you multiply this phenomenon in the surface area of entire Earth, if it had no capillary waves, then most probably the sea surface or the surface area of Earth would shrink. And thus, the transport in and out of gas, and including greenhouse gases, would diminish. Okay? I started my research of using IR spectroscopy. Now, this is some kind of a device, some kind of a technology that can give us a clue of what active groups are present in your sample. I can elaborate on each and every slide later on. What I have is that 3 major peaks are out there whenever you check marine water. It looks like this. Okay? You can see 1, 2, 3. The third one I didn't use. I neglected the data that is hidden here due to the fact that a lot of water vibrations are present in this area. And though it contained a lot of data, I didn't use it. The other 2 peaks belongs to, most probably, they can be interpreted to polysaccharide carbon hydroxide and to amide 1 bond, which belongs to amino acids and proteins. Oh. Infrared spectroscopy. The units are not wave. They are called wave numbers, but they're not. This is energy units. This is not really the wavelength. It's called wave number. So this is why also the chart is diverted. Yes, it should be here, but okay. The microlayer is in black. You can see it's all the same in sublayer, 1 meter depth, and in green you can see 100 meter depth. And trust me, I did tens of samples out there in the sea up to 2,000 meters. It's all the same. Those 3 peaks are always there. If you go to the freshwater bodies, such as the Lake Kinneret, the picture is similar, but not really. First of all, everything is clearer. You can see those peaks. You can see 1, 2, 3, but then you have a rise up here of a signal of supposedly carboxylic groups that belongs maybe to acidic saccharides or to humic acids. And of course, you can see that the microlayer sample in black is always higher. And trust me, you can try that. Let's talk about polysaccharides here on the right. Well, polysaccharides are to be blamed, to make a long story short, they're the one to blame for this surfactant activity in a direct or indirect way. The thing is, though polysaccharides are really just monomers of sugar that are just connected one after the other, this is how you get some kind of a chain of saccharides. Not to be confused, by the way, with polysaccharides in our body that are branched. Here in the ocean, they are pretty much a straight line, and each sugar of its own, like glucose that you use in your coffee or your tea, is soluble, highly soluble. But as a group, there is a lack of solubility. We are struggling. Those of you who are familiar with this laboratory work, we're struggling for if you want to dissolve gangxanthan, for instance, which is a well-known polysaccharide used in the food industry for muffins and cakes. It's not that soluble. It takes heat to do exactly that. Some words about polysaccharides. Well, first of all, they are secreted by phytoplankton and bacteria. Okay? It's a well-known fact. But the first thing that happens, they are secreted, as I said, as a chain. And from then on, they entangle one another. They make some kind of a mishmash. But then they can create some kind of a gel form also. And the sea surface microlayer is suspected as an entire gelic phase blanket. It spreads over. They can do exactly that in different conditions, such as certain metals presence or salt, high salt and acid. And I'll show you that in a few slides later on. The thing is, sometimes if you look at the literature, they include proteins due to one of two. Either they didn't do the isolation work very well, or the fact that they are sticky. These polysaccharides are very sticky, and we suspect that once they aggregate, they can incorporate some kind of a cargo, a hydrophobic, hydrophilic. It depends on the polymer, but they can do exactly that and create certain aggregates that can either sink or ascend and float. Depends on the density. I tried to do some kind of isolation of such a polymer. I used these two candidates. This is Aphanizomenon, which is a cyanobacteria, well-known one, and Senedesmus, which is a freshwater green microalgae. You can see it's a tedious work, by the way, to isolate it. At the end of the day, you've got the polysaccharides peak, the carbon hydroxide, and the supposedly carboxylic groups. And I took this, let's concentrate on this one. I took the Aphanizomenon polymer. This is IR spectrum, by the way. And I put it in a bottle, and I rotated the bottle in 3 rounds per minute, very, very slow, for 2 weeks. That's an exaggerated time, but still I could see by using dynamic light scattering device that the average size changed in those 3 repeats from approximately, let's say, 15, maybe 20 to maybe 70, 80. So that's maybe 4 times. And so this is maybe some kind of a proof that they can create some kind of aggregates. It just depends on time, and maybe a hint about them being sticky. I took them out of the bottle. I put them under a microscope. I scrutinized under a microscope like this, and then it's an ordinary microscope, but yet a bit different. I used two slits. It's a very cheap. You can buy sheets of slits in 50 shekels. What actually I did is, and it's not my invention. You put one slit like this, another one like this. Then you have 90 degrees. Then only light that can penetrate through these bodies and then make this half a turn of 90 degrees can penetrate through the slits and into our eyes. All the rest is black. Trust me. And then you can see those recreated gels or polymers that are called, if you're familiar with the term TAP, transparent exopolysaccharidic or exopolymeric substance. There are a lot of names for this, or EPS, which is exopolysaccharides. They are all transparent. They didn't know how to call it, so they call it transparent polymeric something. But under the microscope, some of them are pretty much visualized by the naked eye. Then I added some calcium chloride, and then you can see them shrink, and after a few minutes they even shrink further. This one implies just, it's not a proof, but if I take it back to the first year laboratories, if you know, there are some compounds such as EDTA, which is a chelator, that can grab on calcium ions due to the fact that it has two carboxylic residues connected to two tentacles, exactly like I assumed as I saw the spectrum of the IR of this certain polymer. Okay, field samples. If you want to see anything you want, any phenomenon, not any phenomenon, but a lot of phenomenons, physical phenomenons that you want to test for yourself and to have evidence or a clue or a hint, starting with fresh water gives you a real high benefit due to the fact that some of the phenomenons are more robust. And so on a rainy day, or after a rainy day, you could see this, I don't know if you can see that, but there's some kind of stretch of brown streamline of, clay. And that is just to say that there is a good flush of water from the northern Jordan entrance, the Jordan mouth, and into the lake. Then I sampled 1, 2, 3, 4 stations for polysaccharides. I skipped the part where I show you how I test the polysaccharide, but trust me, it's a very good one. Immediately you can see that there is some kind of a gradient of polysaccharides starting from the mouth of the Jordan and into the lake. While if I can borrow the term stratification, the difference between the microlayer and 1 meter below, which is here in red, is not that good. This is all sublayer, 1 meter depth, and microlayers of stations 1, 2, 3, 4, starting from the mouth and into the lake. The reason is maybe I suspect it to be that although we think that the Jordan River, as the Bible says, is like the Mississippi, but it's it's tiny. Well, when there's a rainy season, you can stand on the river mouth. It's less than 90 centimeters. There's a lot of turbulence. Maybe the microlayer is not that developed yet. Okay. Another source that I've found in this same aquatic body is algal bloom. Are you all familiar with the term? More or less. Okay. So algal bloom, just a few words. That's just some kind of event where there's a lot of solids that created due to the bloom of micro-algae, and it could be very well in the size of the Kinneret, or it could be in the size of Ireland, and you can see pictures of those out there in Google. The thing is, some of them are very, very toxic, and they can contaminate the water that you drink until you can, well, sometimes you can even die if you drink at the wrong season or before treatment. This is the reason why it's monitored here in Israel, in the Kinneret. They take place each and every spring, once again and again, and they are also it is also monitored elsewhere in the world. Again, sublayer and microlayer. You can see that there is a great elevation in the concentration of polysaccharides in the springtime, whether you could not detect it in the sublayer. So there are two origins of polysaccharides that are well known: the river, Jordan River, and algal blooms. Okay, from now on, all the slides deal with approximately 1,000 kilometers, 400 meters, off coast Shikmona, and up to Bat Galim. The thing is, it's a great opportunity to study an area that is influenced by urban runoff maybe, and rivers such as the Kishon, and of a coast, and the Mediterranean coast, etc., 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 and aerosol, you name it. The results here are interesting also. Whether while in the sublayer you can see almost nothing the entire year, or in the winter season especially, you can see that in the microlayer, and trust me, these are rainy days of 2000. All these data come from 2015. They were accepted after rainy days. So there's some kind of an elevation in the concentration of polysaccharides, but it depends on, well, it is highly influenced, I think, on rain. This one on the right, okay, here doesn't, something happened there. Peleg. Okay, sorry. This one on the right belongs to something called slick. A slick is some, I don't know if you're familiar, it's some kind of, it looks, an exaggerated picture looks like this. Okay, I can show you that. A slick is some kind of an area where you have, though you can see the wind is forming, everywhere it is forming ripples and small waves as we discussed earlier on. In this spot, which could be very well in the size of 50 by 50 meters, there's none. It's just flat, and so it's easy to detect. Okay, this one kept on going. Okay, this is an exaggerated, but you can see that there are a lot of ripples due to the that were created due to surface tension plus an airflow such as the wind. But in the slick itself, the surface tension is lower due to the fact that there are surfactants. And you can see, what do you know, the polymers concentration are much higher. Sorry. What? What?
From the boat.
Yeah, this is just a representation, just a sample. But yes, you can see it with the naked eye. It's not that intense as this one, but yes, you can see that with your eye. You can Google it and you'll see it straight away. Yeah, the spot. No, this is a spot of surfactants, of organic matter that all join together, and it is, for some reason, it is caught up in some kind of a spot that will disintegrate eventually. But you can see that it's a great spot. It's like you pour some kind of an oil on top of the water. Yeah, sea strips. The strips are most likely caused by boats, I think, that just passed and just they either polluted the area or they create some kind of nicks maybe in the water surface. I don't really know. But this one has nothing to do with the boat. It never passed. Also, the same one is here. This one really happened due to the fact that if you're familiar with this phenomenon, each and every year when there's a highly rainy season, the drainage system overflows. And so they don't really know what to do with the water. For some reason, they just discharge the waste and into the water, and all of a sudden the slick was formed. So I thought it's a good, everybody, all the researchers on their bikes like this and went to sample the slick. So that's exactly what I did. Okay? Okay, this one can take me only so far. These samples can take me only so far due to the fact that they are very tedious. There's a lot of tedious work to be done. And at the end of the day, you end up with something like a few milliliters. So this is why I had to build this monster. Okay? Can you see this one? You can't see this one. Do you have a reason why? הם ב-F7. function F7. Get it? Okay, maybe. Okay, maybe. Now you close the PowerPoint. Good. Okay, this is the microlayer. Never mind. What's actually what you'll see here is some kind of device that has, it's a medium tech. It's not a low tech, but it's not a high tech device that I built. What you see here is a cylinder, a glass cylinder that rotates. It's a super fast one. I used 3 rounds per minute, but it will show you the principles. It's good enough. Most of the water that are seawater will drop down, but some of it will attach to the surface of the glass cylinder, and then will get gripped by the gripper that you see above. Then in a passive way, they will pass to the bottle that is collected beyond. Okay, this is a merely representation, and that is how you scrap the surface of the film that has been attached to the cylinder, which is made of glass, exactly the same that it was a glass plate. This is how it looks up in the sea. This is a bit of a אוקיי, אתה יכול להחזיר לי את הפאורפוינט? מספיק. It's not a medium, it's a low tech. It's a medium low tech. Okay. Okay, what I started to do is אתה יכול לשים בסוף? What I started to do is, the first thing I did this work with a collaboration of my friend, Eyal Rahav. And what we did, we don't have a lot of time to explain, but since it's been published, there's no problem. We took some measure, and the most important one that the highlight of this experiment was the activity measurement. Are you familiar with primary and bacterial productivity? Okay, so we measured primary productivity, which is the assimilation rate of carbon dioxide at the end of the day of phytoplankton, with and without an additions of aerosol that I sampled. Okay, we sampled aerosol that was taken in September, the very same year, and we added in a more or less the normal concentration of aerosol in a case of a dust storm. And in here you can see that in white boxes, you can see that there is not a great change without the addition after 48 hours of primary production, but there's a slightly elevated after 48 hours or even less if you use the addition of an aerosol. This is the picture. This is what happens in the subsurface layer. When you check the same conditions in the surface microlayer population, you can see that there is a slight difference. It's a bit higher, but it's not that okay. It's slightly higher. If you look at bacterial production, which is the assimilation or incorporation of leucine, which is an amino acid, into bacteria cells, you can see that after 48 hours without any addition, there is almost zero. Doesn't matter what population you use here in white boxes. But then when you add some aerosol to the samples in the SSL, that is to say 1 meter depth water, you can see a slight elevation in activity, but in the surface microlayer, the elevation is much more emphasized, up to maybe 5 times the starting activity or bacterial productivity. This one gives us the assumption that these bacteria cells, well, they are somewhat opportunistic. And so if they have some kind of nutrients income, they will use it and use it by far faster than other population in the rest of the water column. Though we checked only, to admit, only 1 meter depth populations. Okay, the rest is not that important. You're more than welcome to look in the net. Okay. Then I went on to look, to try and to analyze the distribution rate of the different compounds that are there in the microlayer. Well, if you remember what I showed you there in the second slide, I took olive oil and you took water, and the mixture they separated just due to 2 different physical characteristics. One of them is that the olive oil is not soluble in water. The other one is that it has a lower density. So solubility and density determines the distribution of different molecules. It's easy to show that it's the same way with limonene. This molecule, which is rather hydrophobic, and its density is lower than 1, it was found in the microlayer only, the SML. Well, on this fellow here, it's slightly less clear. The density is somewhat close to 1, but it attaches to particulate matter. I know that by filtering the water or using crude water, then I could cohere what is the fraction of particulate matter. And it didn't dissolve in 1 meter depth. So that's a bit unexplained. This fellow looks like a surfactant. It has a nitro group here, which is rather polar, and a hydrophobic tail. And thus, it was, the density is somewhat 1. I suppose that it could be it might be found in the microlayer, but it wasn't. It was only submerged in various samples that I took in the Mediterranean. Many pesticides and herbicides that we monitor all the time, they have very low solubility. One good example, for instance, is DDE. That is, as an ex-farmer, I can tell you that is the reason why we use, in agriculture, we use surfactants in order to solubilize these compounds. DDE, which is a derivative of DDT, those of you who remember the first immigrants that came to Israel were sprayed with DDT. Also soldiers from the Second World War in order to disinfect pests. These compounds are banned in the world more than 40 years and are not used in Israel also. Still, they are there in every fish sample, crustaceans, in whales, in dolphins. Whatever you bring, it's there. The density is lower than 1, but it's almost never found in the microlayer. In sediments, yes. In the microlayer, not. So most likely, it is not that good explanation, and you can move on, try to elaborate or to cohere something else. Just adding to this fact, all these compounds that are rather hydrophobic and they don't dissolve in the water, they have density of more than 1. They should have synced, but they didn't. So what I decided to do is I tried to do a thorough test or exploration, a very vast one, using a GCMS in order to determine exactly what compounds are there, using the details if you seek for the details of sampling. This is more or less. And then for each sampling spot, I had 4 different samples for each and every point. One of them of microlayer, after filtration and before filtration of 0.2 micrometer filter, and the same for the sublayer. Okay, we don't have a lot of time to discuss this one, but at the end of the day, many compounds were found to be present the entire year, but some of them we don't have the time to discuss. It's very interesting, fascinating, but we'll discuss phthalate and BTEX. In this, I took the advantage of sampling also aerosol samples by concentrating them on GFC filters, if you are familiar with this work. And what I found, we don't have a lot of time to discuss this one. This is called principal component analysis. At the end of the day, it breaks down a lot of data into only 2 factors. And you could very well see that some of the compounds, if you're familiar with this work, are elevated or they are strengthened in specific seasons. And some of them in the summer, some of them are in the beginning of the winter and high winter. Okay, I can elaborate on this one later on. BTEX, we mentioned these 2, so let's look at them. BTEX is a monocyclic aromatic compound, or a group of compounds. They all look like that. Okay, benzene, toluene, ethyl benzene, 3 forms of silane. They are all carcinogenic, and so they are monitored everywhere in the world all the time. Okay, they are produced worldwide, more than 40 million tons. How much? 5. Wow, that's not a lot. Okay, the density is of all these compounds is lower than 1, and they end up in the combustion system. The thing is, they have high vapor pressure. That is to say, they're volatile and they have low solubility. I found them in mainly in the SSL particulate matter, that is to say 1 meter depth, submerged in the particulate matter, while on the sea surface microlayer they were all dissolved. My assumption is that they have a greater attraction, if you like, for the air. So once a particle sees air, it will for sure leave into the air, but when it's submerged, it prefers particulate matter on water. Also, the conditions in the microlayer could maybe push to dissociation from these particles, a lot of wind, waves, and sunlight radiation. They were also found mainly in December, maybe due to urban runoff. Phthalates, the second component, is also monocyclic. It has only 1 aromatic group. I don't know why that's the major components, but that's the way it is. They are all residues of plastic industry. And, well, they're not covalently bound to the plastic. And so at the end of the day, they dissociate from the plastic. And whenever there is a plastic, you'll find phthalates. These compounds have higher polarity. They're more polar. They have lower vapor pressure. They're less volatile. The density depends. Some of them are higher than 1, some lower. They are also suspected as carcinogenic, and so they are monitored, but into a lower extent. This is interesting. It was found mainly in the SML, floating in the microlayer, but some was found also in the 1 meter depth. And eventually, they have higher solubility, so it makes sense. But they have lower volatility, so they never evades to the air. Highest concentration were again found in the winter time. And if you try to look at these compounds, it was interesting to see that the Kishon mouth, the Kishon as an origin of phthalates is a very good one. You can see that I sampled the Kishon mouth only in the microlayer, and you can see that it brings on a lot of either plastic residues or you name it. Also, if we remember the slick formation was also in the same sample where I found great concentrations of polysaccharide. I found phthalates also. It makes sense, maybe due to, I can explain this one, maybe due to the reason that they are sticky and they can take on some hydrophobic cargo such as phthalates. Few last slides. Aerosol. Aerosol is being monitored, but not by us. This one, what I show you here is a model that can go back to find where did this stream of air came from in the last 3 days or even longer times. I sampled it in here in Haifa, in Shikmona. I just concentrated the air on a GFC filter. And then you can see that these are all 3 different altitudes of air that all concentrated into here. You can see that in this very day of July, though the annual average was 31.7, it raised up to 156 in this same day. And we can say pretty sure by using this model only that most likely the air came from somewhere, maybe Turkey. Well, you can see for yourself. It's not the holy truth, but it's some kind of a model we use. More interesting example is here. There was a dust storm in 2015. I had the chance of sampling the water plus taking aerosol samples. And then you can see that in the aerosol itself and also in the microlayer only, you can detect an elevation of BTEX in this case, which is high pollution. And you can see where it came from, though the BTEX could join this stream of air in these altitudes everywhere. Okay, don't have time. We talked about sticky aggregates. This is the last slide, maybe just to show you the potential of the microlayer. The thing is that some particles or some molecules cannot sink. They are not that polar, such as I showed you olive oil, and so they can stay. They are trapped on the microlayer. Aerosol is being created from wave caps. That's the top surface of the sea. So it includes a lot of parts coming from the microlayer. And so if parts are being pushed or created as an aerosol, eventually it will transfer, well, a few kilometers, maybe tens of kilometers, maybe even more. Could be hundreds of kilometers. But then at the end of the day, it will sink. It will sink. It will sink, and then the next wind gust will come, and we bring them up again. These particles are fairly hydrophobic. If it's a particle, a whole particle, or a soluble or an insoluble molecule, it will be trapped on the microlayer and move further ahead and ahead. That's it, I guess.